plus B 7 CLC. Okay, clear the screen. You can do all kinds of calculation. 12 multiplied by sine 3 times pi. Sort of calculation like this you can do. You can do matrix calculation like making the matrix like 1, 2. This is the second row. 3, 4. Okay. You end up with this matrix. So this is a very powerful code. You can do much more in finite element course. Alright, I will push you through that far. So it is very good to construct 2D, 3D plots. Generally in a thesis we prefer the figures and its plot in Matlab rather than Microsoft Excel. It is quite crappy. You cannot adjust the size in the pixel. Okay, if I want the 300 by 400 pixel of the figures, okay, of the plot, then you cannot do it in Excel, right? But in Matlab you can adjust everything. You can put the sign like the alpha sign, Greek letters, symbols. It could be there. Okay, so it is extremely powerful. I use it for most of the applications that I have in my life. Okay, do the graph, do command lines, and this. Okay, it's clear. But first of all, what you have to do is to just set up some directory that you're gonna put your work in. Okay, so here is a directory that I set up. Okay, you can select over here. Okay, I will not go down into that level. This Matlab is pretty old. This is 2009A, so well old but still good enough. You don't need the 2017 version. Okay, even for 2002 you cannot use all the sometimes you don't use all the commands that they have. But anyhow, well the newer version you have, the better. Okay, you may not need to install all those toolbox that comes with the package, because the toolbox generally for some specific applications, sometimes for signal analysis, sometimes for image processing, sometimes for the biomedical or aerospace kind of things. Okay, so maybe statistic toolbox. Okay, so if you don't think that you're going to use those toolboxes, then you can opt for like you can uncheck all those toolboxes and then you don't need to install, because Matlab's going to take your CPU and also take your hard drive a lot. When you run Matlab, you can see that your CPU is almost like it does nothing more than just Matlab. Okay, so if you are browsing Facebook or do other things, okay, just close those programs down and then let the Matlab run. Well, in this course, structural analysis, you don't find that Matlab is going to take you so much resource. But once you get into finite element analysis course, well, we will be talking about the huge numbers of degree of freedoms, okay? And your computer will slow down quite significantly, alright? So it's not something like you type in, hit bang, and then you get the result. You're gonna wait for a while for calculations. Alright, so you execute everything within this command window. This is something that is in your directory. So if you have the code, M file whatsoever, construct over there, it will be listed off over here. So you can do the file new. Okay, so this is like a new M file. Okay, so we're gonna do the new M file. With the new M file, you come up with something like this. So for a new M file, you will put those sets of commands in the M file such that ขอบคุณครับโหลหูกระเป๋าพี่อ้อดังเหรอ so we will put sets of command, alright, and then with sets of command, we call it like a program or functions. Okay, so to start it up, yeah, you're gonna have functions. You put the function name like, for example, today we're gonna do maybe stiffness matrix of the frame. So I call it FSTIFF. Okay, name it in the way you want. In the frame stiffness matrix, if you want to end up with element stiffness matrix, so okay, this in the bracket will be the outcome, okay, that you will obtain from running these functions. A good practice for programming, if you put the percent sign and when you type whatsoever behind the percent sign, it will not be executed as the command in Matlab, it will be just a note. Okay, so if you want to note down something for yourself, for you to understand, like, okay, this variables is what, okay, then you can put the notes over here. I will put generally my notes just like this. So the first variables we have KELE. That means element stiffness matrix. Okay. For frame, alright? Okay, you can use uppercase, lowercase, it works. But Matlab is case sensitive. Okay? Matlab is case sensitive, so the capital letter F and lowercase f, they will be two different variables. Alright? But I mean, in the comments, okay, you can write it in the uppercase, lowercase, it doesn't really matter. But please keep in mind that Matlab is a case-sensitive program. Some other programs like Fortran, Pascal, those programs may not be case-sensitive, alright? But Matlab is case-sensitive program. So, okay. What do you want from what do you want to establish a stiffness matrix of the frame element? You're gonna need area. You're gonna need INER. Okay. So now you need to explain, right? Area is cross-sectional area. INER. I always use the variables name made of 4 letters, 4 characters. So it will look just neat. INER means second area moment of inertia. Okay. What else do we need? Length. Okay, I will put LENG, length. What else do you need? Alpha. Okay, so this is going to return your stiffness matrix in global coordinates. So you need the orientation of this element. Okay. Well, as we do more, we're gonna find that maybe if we need any more parameters in here. So area in here, ANG means the length of the member. ALPH means what? Orientation, which is refer to the x-axis. Alright, so whatever, okay, if you have more and more variables, this is just looks nice. You don't want to put it like this or not, okay, it's fine. And by the way, programming is the art. It is not the pure science, it's the art, okay? So you can write the program in a different way, of course, all right? Well, as long as you end up with the same algorithm, same idea, same thought, same logic, so okay, we come up with the same analysis result. So, okay, there could be many techniques. I may use for while, I may use for loop, you may use while loop, okay, possible. Alright, so first of all, we need to establish the element stiffness matrix. Let me do it this way, K-glow. It is the element stiffness matrix for frame in global frame. Right? That is K-glow. But I will have KELE, which is the element stiffness matrix in local. I think that I'm typing local. Location comes up instead. Local coordinates. Okay. Sometimes you type a lot every day, so the finger just goes. Okay, so if you want the final product to be the stiffness matrix in global coordinates, okay, how do you start? Generally, you will need the construction of element stiffness matrix in local coordinates and then conduct the transformation. Okay, so you conduct the transformation from your local frame into the global frame. Okay, by setting up that phi matrix and then times the K times the phi transpose, just like that. So this is the flow. Before you do anything, you just think of this flow. Okay, big idea. Okay, you do this first, you do this second, finally you get the transform stiffness matrix done. Alright? Here is the procedure. So first you need the element stiffness matrix. For the element stiffness matrix, okay, I think we still need this one, elastic modulus. So I name it this way. First, we need the matrix of the size 6 by 6 because this is a frame, right? We will not write the code for the beam because beam is just a subset of the frame. So if you don't want to exercise the axial deformation, it's okay, fine. We can just leave the degree of freedom there. We cannot just, we don't have to use it. Alright, so we need the 6 by 6 matrix. Okay, we need to set this up first. First of all, that element stiffness matrix is a KELE. Okay, so I say that KLELE is equals to the matrix of 6 by 6. Initially, I'm gonna allocate just 0 entries into this matrix. So I set up the rule, okay, the matrix first, but I may not plug in the value as of now. So KELE is equals to zeros. Zeros is a command in Matlab that is used to allocate the matrix. So if I say 0.6 by 6 means you're going to end up with 6 by 6 matrix. So for example, I say A is equals to zeros, maybe 3,4. 3 rows, 4 columns. Okay. So we go back to editor. Alright, now we have KELE 6 by 6. All entries are 0 now. Then we just plug in the entries that are non-zero. So first of all, let us take care of the axial stiffness. Okay, so this is the bar. It's like the bar problem. In the 6x6, which entries are relevant to the axial deformation? 6x6, we generally start with the degree of freedom that is associated with axial deformation, and then lateral, the deflection, and then rotations. Okay, so the first one and the fourth, okay, fourth row, fourth column, first row, first column are associated with the axial deformation. So we will start from KELE. Okay, just to make it quick. One, of course, 1, 4, okay, and then 4, 1, and 4, 4. So each, okay, 1 is what? EA over L. E mod times area divided by LENG. At the end, you put semicolon. Why? Because you're gonna have like so many command lines in the program. If you don't put semicolon, the program will show that execution. For example, I say 10 plus 17, you end up with 27. But if I put over here, it will not show anything. So Matlab will execute the command, but it will not print out. For you, you may not see that it is the critical issue, but for those who run calculations of millions times calculations over here, the computer, you have to spend the resource, the RAM, the CPU, to process what to show up on your monitor, on the screen. That's gonna slow down your PC. So if you don't want to see this command, alright, if you don't want to see how the execution is going on, then put the semicolon there. Otherwise you will see, you feel like you are watching the Matrix movie. Okay, you feel cool, but it's not actually cool because it's gonna slow down your graduation times and others. Alright? In my childhood, when I write a program, I always have something pops up. Oh, yeah, that looks like I'm a boss. but and then my friend said, why do you keep that? It makes your computer slow down a lot. Okay, so we keep that semicolon there. Now, you find that the 1, 4 is actually minus EA over L. So you can say minus, and then you can copy the whole thing. That is one possibility. I will go with this KELE 1, because you conduct that computation in 1, already. If you repeat the E mod times area divided by length, that means another operation. So it's gonna consume your CPU. But here, you just take the value from there and put it here. Faster. And then KELE 1, 4, okay, equals to 4, 1, and finally KELE 1. Done. Axial stiffness. If you want to check your program, just save it like this, and you call the program. The good programming practice, you do it like module by module by module. You don't write like 70,000 lines of command in just one single program. That is the most stupid way to write the program, because you can have so many bugs all over your program. If you cannot test module by module, you cannot find the bug. It's like your car, the engine of your car, okay? The windshield wiper, the engines, the air conditioners, the fluids that is injected on the windshields, and everything is put in one black box. So once the car is malfunction, you don't know which part. You're gonna look at every single thing in order to fix the car. But when you put things like module by module, you can test the module and you can pick up the module that is likely to be relevant with that sort of error. Okay, so you maybe, okay, maybe these few modules that you need to look at it. But if you put everything all together in one block, okay, it is so difficult to pick up the bug, we call the bug. Alright, so elastic modulus, okay, we can say one area for now, one inertia, okay, you just put one length, one alpha, one, just, so nothing comes up because I don't have anything. So if we say KELE like this, now your entries, those are related to the axial deformation of your frame. Pops up. We have not worked on the part for the bending, the flexures yet. Alright, so okay, looks good. Now you can take the comment out. If you want to comment, you can do it this way. Shadow over the whole thing, right click, and then comments. So you don't need to put this one by one percent sign at every line. And if you want to uncomment it, you want to execute the command, you go to uncomment, and that's it. Okay? So it's quite fast. Now you will be doing the line 2, 2, 3. So you have line number, row number 2, row number 3, row number 5, row number 6. Okay. So row number 2, row number 3, row number 5, because number 4 is for axial, and number 6. Alright. 2, 3, 2, 5, 2, 6, 3, 2, 3, 3, 3, 5, 3, 6, 5, 2, 5, 3, 5, 5, 5, 6, 6, 2, 6, 3, 6, 5, 6, 6. Okay. Alright. So when you start, 12 times E times I over L cube. Okay. Over here, I think my life will be a little easier if I have L cube. I call it this new variable name. L cube equals to LENG times LENG times LENG. and L square is equals to LNG times LNG. Alright? So I do the L3, okay? L cube, done. This one, 6 E I over L square. This is minus KELE to 2, right? 12 EI minus 12 EI, and then this is KELE to 3. 6 EI over L square, right? 2, 3 is a 6. Oh, 2, 6, 2, 6, 2, 6. Great, thank you. And then this is equals to KELE to 3. Okay? Maybe just look at it first. The second line you have KELE to 3 and here, right? 6 and minus 6. This line you have 6 here as a minus sign also, and then the 6 here as a minus sign. This one you have the 6 and the minus 6, right? Okay, for 12, any other 12, just copy, and then 12 will be minus 12 here and plus 12 there. Okay, so no more 6, no more 12. Now 4 and 2. So this is equal to 4 times E mod times inner over L. Okay, and this one is 0.5 times KELE 3. So 3 will be there, and 3.6 is going to be there. All right. Save, and then execute the command. You just go up like this, okay, to review the old command that you have used. All right. Do you see KELE comes out quite so many times? What is going on? I didn't put the semicolon there and semicolon there. Okay, so it comes up to many times. And imagine if I didn't put at any point, you will see so much fun. So okay, CLC clear the screen first, and then alright. 1 EA over L, 1 E minus 1 EA over L, minus 1 EA over L, 1, 12 EI L cube, 6 EI, 12 EI, 6 EI. Okay, so 6, 4, minus 6, 2, minus 12, minus 6, 12, 6, 6, 4, minus 6. Wrong. And switching, right? It's supposed to, yeah, right? This is 2, this is 4. So, okay, everything looks fine. It doesn't tell you that this program is correct because I just put the EA, all the things 1. So you may try to execute it by having the E some number, A some number, L some number, and then compare with your hand calculations. You develop the program as you are new in this business. You will always believe in yourself, but When you are in here for longer, you will know that the person that you shouldn't trust is yourself. Okay? Because all the errors and the bugs in the programs all comes from you. And you have a very strong confidence that, come on, I checked it already. I wouldn't supposed to make any error. And then 100 of the time, the error comes from you. Okay? So don't believe in yourself. Alright? If something goes wrong, it is your fault. It is not the computer fault. Okay? Computer, the logic is very correct. 0% chance of error. Alright? So it could be syntax error. It could be your logic's error. Okay? But it has never been mathematics. Okay? Error couldn't come from mathematics, from physics, and from programming. So never blame those things. Blame your logics. Blame your syntax. Blame whatsoever that comes from your brains and your fingers. Okay? And I always blame myself to find out the error. Okay? And when you confront with error, when you confront with bug, you will be like, come on, what is going on? You freak out. That is something that's going to happen in your life, like everyday mistake you have. You might not put the glass just right on the spot that you want, so you adjust it a little bit. That's it. So you need to find out the error systematically. The more you write the program, the more systematic thinking that will be improved. Okay. So, okay, now we have element stiffness matrix. Okay, you write the program, you test with manual calculation. If this segment of the program works just well, okay, it might work well in this case, it might not work well in some other case. That is also the possibilities. So, sometimes you test this module, but when you put the module together with other module, or when you put in some different values that you use to test, you still have the chance of the error to come up still, right? So don't have a very strong confidence in anything, right? That nothing could go wrong under your programming. It always goes wrong statistically. And with me, who like always write the program, use Matlab, use Fortran, something always go wrong, and then some bug took me like a year to debug. Okay, for example, some bug that, well, we are talking about mathematics, we are talking about physics, we are talking about the algorithm in structural engineering. Okay, so there are too many things involved in here. You could be wrong at any point. So spare your expectation a little bit that everything could go wrong. Okay, so it looks like KELE seems to work out well. Seems okay. As we test it, it seems good. So we go to the next step. The next step, we have element stiffness matrix in local coordinates now. What is the next point? The next point is going to be the transformation matrix. So it is very good that you put something like a comment, flexural stiffness, okay, over here. When you come back to this code again, you know what you are doing in here. Believe me, just few days later you come back here, you know what was here. And when the code is huge, thousands of lines, you can imagine you have so many things. Oh, what is this? And it takes so much time to try to understand the language of the computer and then interpret into your language. So I put fractal stiffness, then okay, I know that this part is going to be 12.6 minus 12.6. If I don't put anything, okay, what is going on in here? Oh, this is 12.6. This is this one, or this is minus 12. Oh, okay. Alright, so it makes things much easier. Next, okay, we talk about transformation coordinate. Transformation. So what you need in that coordinate transformation? You need the phi matrix, okay? Direction cosine. I'll make it like DCOS. Direction cosine. Okay, the name of that phi. Okay. So direction cosine is equal to 0. See, I use the lower case. I think the upper case, like A equals to, I'm not sure if it's going to work. Alright, so here, obviously Matlab is case sensitive. You cannot do as you wish zeros. When you see the red line coming up, you freak out. Undefined function, how do I do next? What do I do next? I cannot do anything, it's just out of my mind. Read, okay? Undefined function or method zeros for input arguments type double. Matlab doesn't understand this. So, just that, something goes wrong. That's it. Do not send me the email. Alright? I will not debug your code. Okay? That's the last thing in the world you will do, and I will not respond to your email. Just delete. Okay? Waste of my time. So, find out. Zeros, 1. Size of the direction cosine is 6 by 6. You can allocate by this way. D cosine equals to the bracket. It has to be this bracket, not the parenthesis, okay? It has to be the bracket. Let's say if you want to make a 6 by 6, you can do 1, 2, 3, 4, 5, 6. Go to the next line. 1, 2, 3, 4, 5, 6. Go to the next line. 1, 2, 3, 4, 5, 6. Go to the next line. 1, 2, 3, 4, 5, 6. If you have too much time, yes, you can go ahead with this. How many lines? You need the last one. 1, 2, 3, 4, 5, 6. And close the bracket. And then if you put this into this window, okay, you come up with 6 by 6 matrix. Well, if you by chance have an extra zeros like this, let's see, error comes up. So Matlab is a very friendly program. At least it yells back at you saying that something goes wrong, and it tries to communicate to you that this thing is not good. Some other program, low-level language like Fortran, Pascal, C, okay, may not give you this. So I know that error using WordCat. What the hell is WordCat? Go to help, product help, and then find search here and WordCat. What the hell is this? Okay, you ask Matlab, you don't ask me. Okay, sending me the email, waiting for 48 hours, you don't get anything back. You don't know WordCat. You go ask Matlab. Matlab help is very good. It is very friendly. It contains like so many documentations for you. Okay, so you don't need to talk to me. All right. Okay. Come back. So either, okay, one way or another would work. Direction cosine. Alright. What you need to do? Same as before, your direction cosine, you should have the first one, d cos 1 is equals to cosine. Again, cosine of pi, you get a value. It's not cool, you put the capital letter C, get in trouble. Okay, so most of the command are based on the lowercase or lowercase. If you put the uppercase, you will be in trouble. But you can name your variables with lowercase or with uppercase. For example, if I name the variable a, b, c equals to 1, yes. Let's try a, b, c. Would it recognize? No. Okay. So it is this sensitive. Okay. Cap A and cap B and lowercase c is different from cap A, lowercase b, lowercase c. Cosine of what? Yes.
Can you scroll up, please?
Okay. Yeah. Sure. Yeah, you just let me know because I am on my screen, so I'm okay. Alpha. That's it. So, what next? 1, 2, etc. Okay, your job, not mine. Finally, you need K glow. That will be equals to direction cosine matrix multiplied by KELE multiplied by direction cosine transpose. If you don't know what is a transpose, how to put that transpose in your matrix transpose. Okay, and then check. Oh, transpose is this one here. Alright? So MATLAB Help is much better than Excel, Microsoft Help, other program help. Documentation is very solid. It has the examples, many things in there. You can learn quite effectively in here. Okay. Now you're done. So, yesterday you have that homework, right? That homework can be cross-checked using this MATLAB quite easily. Well, nothing for you left here. Just complete this. What? How many more lines? You have 1, 2, 3, 4, 5, 10 more lines. You're done, right? You write more, 9 more lines. Okay, from here. So d cosine 1, 2, and then 2, 1, 2, 2, 3, 3, and 4, 4, 4, 5, 5, 4, 5, 5, 6, 6. Done. And then you just put in the figures in there and run. So that's it. And then you put everything 1 but alpha. Okay, so you can test with the alpha like 30 degrees in comparison with 210 degrees. Okay, and then you can check with the stiffness matrix. So I need alpha. Okay, I don't write it this way. But then I give you this code. Okay, I give you this code. You just put everything one, so the EI everything one, okay, EIL1, but just alpha being 30 degrees. If you have the starting node at here and then ending node is there, so you have 30 degrees. You will compare with a case where you have 210 degrees and then you switch the ending node and starting node. Okay, so this is what I want you to do with the code. If I just show and then, okay, do you learn anything? Yes, I think I understand it. Okay, and then you never touch this code. Really, you can. At the time that I need you to touch it seriously, you don't get it. Okay, so this is the first thing. Second thing is that this is the code for the frame. I need you to adjust it such that it is for the truss. Okay? As a matter of fact, you just truncate things down. You just make things smaller. Should be easy. But you should understand this line, that line, how things work. Okay? If you start yourself from writing a new code, that is quite good. Okay? Now I show you the more difficult one. I ask you to do just the truss member, which is much more easy. Okay, much easier. So do it. If you want to start from watching the video another time, so you get it, oh, okay, yeah, we make a flow like this, and then you write it by your own. It will be, I think it will be easier than just get this code that I will send you, and then try to delete, oh, I don't use this line, do I need this line, oh, and then I adjust this, adjust that. It will be more difficult to write the existing code. But you can try, and then when you run, you come up with bugs. Okay, so you have two things to do for the frame. Okay, just execute the command and compare with make use with that thing you do by hand, and reduce this code down to the truss level, not the frame, truss. So you just have the x and y, ux and uy, you don't have the rotation. Final matrix turns out to be 4 by 4, element stiffness matrix of 2 by 2, transformation of 4 by 2, okay, and so on, right? So it is the easier procedures for you, but these easier procedures will enrich your understanding. If you don't understand the other one, then it is difficult to make the easier version for the truss. So these two should add up to should add up. Okay, so deal all together on this Thursday. Okay, come on, you don't laugh. This is just 6 more lines to complete. What else? All right. How could it be difficult for you? And then you have seen these operations. So to make something easier, if you understand this thing, you can do the easier thing. I am not doing truss and ask you to do the frame. Okay? I do it in the reverse fashion. So I show you the frame and ask you to do some easier thing, which is a truss. Okay? Alright? So I'll save this file and send to your email. Wait for an email, 10 minutes probably, and then you can start doing these things. Right? Okay, so your structural dynamics is short for today. Okay?
Sir, can you make the assignment question clear? We are not clear what's the assignment.
Not clear about
Assignment question.
assignment.
Yes, that's the question.
Okay, what is the question?
Like what you give, we aren't clear about the assignment.